a number of challenges, and one of the most significant aspect for that, what I feel, is the increasing population, because our population is almost 7.8 billion as of yesterday, and it is growing at a rate of about 81 million per year. And not only that, our expectation, comfort level and expectations are also growing, because our spending levels are also increasing. So accordingly, our energy needs are increasing. Initially, you may be having a cooler, then you must have purchased a AC. Later on, you must have purchased a second AC. Like that, your energy requirements are increasing, and everything needs power. But unfortunately, our fossil-based natural resources are depleting at a very fast rate. And these are all definite and not sustainable. And because of that, various political and non-political aspects are also cropping up. We are facing a lot of challenges like increasing cost, and availability is becoming very difficult, and we have to depend upon foreign nations for getting petroleum product. Another aspect is the challenge, because wherever or whenever we are using fossil carbon, hydrocarbons for generating power, naturally there will be carbon related pollution, because hydrocarbons and the pollution, you cannot avoid that. And we all know the impact of the hydrocarbon pollution, that is the carbon dioxide, carbon monoxide, etc. We are facing a lot of challenges with the pollutions and changes in the weather patterns, etc. Now, this is the latest population chart. Just yesterday night only I have updated. As I told you, it is 7.8 billion. And that our contribution, our country's contribution is 1.38. China is just a little above us. And what I feel is maybe within about 15-20 years, we may actually supersede China also, as per the current rate of population growth. And this is the typical plot of the world power generating capacity as published by International Energy Association. This data may not be 100% perfect, because some countries may not be updating their generation data as per the requirements. Some data, maybe if you see the detail about that, some countries' data may be representing 2012 data, 2016 data, like that. But we can consider it as about 7,200 to 7,400. Say, let us consider 7,200 gigawatts. And out of that, nearly 65% is contributed by the conventional fossil-based resources like solid, gaseous, and liquid fuels, coal, gas, and oil. And about 10% is contributed by the nuclear power plant, and the remaining nearly 25% is contributed by hydro, including conventional hydro. Renewables, including conventional hydro. Out of that, 16% is hydro. So you can see that the new renewables like wind, solar PV, biomass, small hydro, geothermal, etc., their share is very, very less, hardly about 10%. This is the status about the electrification, household electrification worldwide. This data I have taken from the World Bank site, and you can see that around 10% of the world population still doesn't have access to the grid connected electricity. And that figure is actually that the gap is coming down, but you can see the data for nearly 20 years, because this particular data I regularly used for various purposes. So that gap is coming down, and if this trend continues, it may take at least 30 to 40 years for meeting that 100% requirement. This is the world profile, and this is our country's electrification, household electrification data. You can notice that nearly 99.93% households in our country could be electrified, and 0.07% that is yet to be electrified. And this status is maintaining nearly for the past 1.5 years. And that particular location, that is Chhattisgarh and the related area, on that nearby areas, it's a very hilly area. A lot of tribals are there, far away from the grid centers or transmission lines, etc. So it is very difficult to electrify those locations. So how we are going to electrify or how we are going to provide electricity to those remote communities, unfortunate people, maybe some 10 families or 20 families. So these could be possible only with the distributed generation using renewable, because conventional grid 11 kV system or 33 kV system, it is impossible. Nobody will extend a 33 kV grid for a 5 families staying in a remote tribal area. It will not be possible. So this is possible only with the new technologies, that too distributed renewable energy. Now this is the status of our current resources. Currently we are generating block electricity mainly from coal and hydro system. And their generation trend, you can see more or less maintaining some ups and down, but not much deviation from the standard value. But see the nuclear and oil. After that, the Japanese nuclear incident, interest in the nuclear is coming down drastically, and many nations are now decommissioning nuclear power plant, and oil and gas. Stock of these resources are fast depleting. And as per the latest published data, oil and gas will last for about 40 to 60 years. And even the people who are staying in Gulf countries, because I have visited a few Gulf countries and I know certain people, I mean locals also. So they themselves say that they already started installing solar PV in their rooftop, RBs, where the oil is very cheap. Because this oil and gas, as per the experts, it will last for about 40 to 60 years only. There may be some plus or minus, of course. So what they expect is, once these oil and gas stocks are completely exhausted, those systems which are currently running on oil and gas will switch over to coal. Now the current data about coal is going to last for about 150 to 170, 80 years. That is the status of coal, world coal. But if after this oil and gas is completely exhausted, when these systems switch over to coal-based, primary energy, then in that case, it is expected that by the end of this century, the coal stock will also be completely exhausted. So in that case, what is the next step? Then comes this problem, that is the pollution related from, associated with the hydrocarbon. Now nearly 41, 42, 43%, actually these figures are continuously going up and down. Nearly 42% carbon pollution is attributed to thermal power plants. And nearly 23, 24% carbon pollution is attributed to road automobiles, especially these cars, trucks, buses, etc. So nearly 65%, 66% of the carbon pollution is actually contributed by this hydrocarbon, that is coal, oil, and natural gas. So if you can switch over these resources from coal to some other green or renewable based system, naturally we can reduce the pollution, because this is a very significant concern everybody is having, that is the carbon related pollution, because our weather patterns are changing and breathing problem. Those who are regularly coming to NCR area, Delhi area, etc., you may be aware that we are always facing a lot of breathing problem because of the open burning of the agro residues. So the question then comes, so if you want to remove this coal, avoid this coal and other hydrocarbon, fossil-based hydrocarbon, then what is the next? Answer is very clear. It is renewable, because as long as sun is there, earth is there, renewable energy will be there. And renewable energy is distributed. It is not like that it is only available in Gulf countries or some other countries. It is available everywhere. Some renewable will be available at any location, every location. It may not be sufficient to meet all the energy requirements of that particular area, but something will be available everywhere. It may be solar light, or it may be wind, or it may be small hydro, or it may be biomass. Something will be available. So we have to find appropriate technology to generate power from these resources. And what are those resources? There are nearly about 10 to 12 different technologies currently available. Of course, if you go through various textbooks, you may find different categories, but I elaborate as much as possible so that it will be easy to discuss as well as understand. So there are biofuels and biomass. Biofuel means something like that, some oil extract, maybe coconut oil or those kind of oil, jet rofa, etc. Those can be used for replacing diesel, the so-called biodiesels. Then biomass is basically something like a firewood. All agro residues are firewood, and in some of the NTPC thermal power plant, because it has become a mandatory requirement in case of NCR area, we already started co-firing. Nearly about 5 to 10% of biomass, mainly agro residue, will be blended with the coal. And that technology is being developed so that this open burning of this agro residue can be reduced. And then comes geothermal. Geothermal is basically the underground heat energy. Enormous potential is there, but everywhere it may not be very economical. There are locations where it is very economical, but there are other locations where it may not be economical. Then comes the hydro. Hydro means small hydro, not the dam-based conventional hydro. Because when you consider hydro under the renewable, usually it is the small hydro system. Typically few kilowatts to maybe less than 10 megawatt capacity or in that range. Then hydrogen energy. Hydrogen energy is the future energy because there is a terminology associated with that. That is the hydrogen economy. We are shifting gradually from the carbon economy to the hydrogen economy. Then comes the solar energy. Under that, fundamentally, there are two technologies. One is the photovoltaic technology, second is the thermal. And under solar thermal, there are n number of technologies. N number of technologies are there. So that is having good potential. Then tidal energy and wave energy associated with the water bodies like seas, oceans, and rivers. Tidal is basically the level difference, and the wave is basically wind acting on the surface of the water bodies. And finally, it is the wind energy. Out of this, some of these technologies are more matured, relatively more matured as compared to other technologies. For example, solar photovoltaic and wind energy technologies are well matured, but solar thermal is getting confused whether should I say it is matured because it is very expensive, almost 20 to 25 crore per megawatt solar thermal. Maybe it is matured, but the technology is very expensive. Then hydro is not very high, very expensive, but the problem is some of these technologies are location specific because you may not get find the hydro potential everywhere. Especially this is a very well available in case of hilly areas or extreme rainy area, etc. Then biofuel, that is a good choice because more or less everywhere you will find some biomass and biofuel. Hydrogen can also be generated in a distributed manner, and tidal energy, that is because of the level difference due to the attraction between Earth and other planets. So there are countries, there are locations where the tidal energy potential is very high because the level difference will be extremely high. But it is not very good in our country because the level difference, that is high tide and low tide difference may be hardly about 1 meter or around that. So that is not a good energy potential for our country. Then of course geothermal. There are, I'm not very sure because earlier NTPC was having a program to install a geothermal program somewhere in Chhattisgarh. But it is very expensive. So currently progress is very slow, but it is not abandoned. That program is still effective, but progress is very, very small because of the cost. Because the problem is geothermal, if it is natural water available, hot water available, technology will be somewhat economical. But in our case, normally we have to force pressurized water underground, and then we have to collect back that water. And that water which is coming out from the underground, it will be highly corrosive. So we have to actually have secondary heat transfer systems and cost will be anyway going high because of that corrosive atmosphere. That is a big challenge. So these are some of the resources we are focusing on for meeting our future requirement. Among these, the first two, that is PV and wind, are the topmost among all these, and other technologies are some of the technologies are working in commercial, but many of the technologies are still under laboratory level only. Then fuel cell is basically the energy conversion mechanism from hydrogen directly into electricity. Small hydro, probably some of you must have seen it in hilly areas, because the advantage with the small hydro is we don't require a reservoir for storing the water. It is basically a runaway water system. It will be channelized through a piping to a small impeller. Then it will be driving a small turbine, generator, maybe 2 kilowatt, 5 kilowatt, etc. IIT Delhi, few years back, IIT Delhi MTech students made a few projects under financial support from Ministry of Defense, and they have made small hydros on 3 kilowatt, 4 kilowatt systems, and installed in the Jammu Kashmir area a few years back, nearly 10 years back. And that was sufficient to meet the requirements of small communities, maybe some 5 families, 8 families, like that. And hardly 2 to 3 hours only those systems remain in service. Biomass, it is actually getting a lot of attention because of the pollution. Wave energy and tidal energy potential in our country is not very good. Those who are interested, kindly go through the YouTube. You will find many videos of these two technologies. So as of now, the world energy consumption by various sectors, you can notice that industrial and transport sectors are consuming maximum energy. Nearly 80% of the energy is being consumed by industries and the transportation sector. And the share of renewable in these two sectors is not very encouraging also. Especially renewable share in transportation, you can see that it is hardly 3.3%. And nearly 80% of the total energy is still coming from fossil fuels only. So it is a big challenge for us to change from these fossils to green energy system. And the share of renewables in power system is relatively better. Nearly 27% of the world power is contributed by the renewable. That includes conventional hydro, nearly 16%. So around 11% only the new or modern renewables like wind, solar, etc. And this share is going up. And the world target of renewables in the power sector is 30% by 2030, year 2030. And in our country, our target for 2030, renewable in the electrical sector by 2030 is 40%, 10% more than the world target. And this is the current status of the world renewable. Top 2 renewable. Wind is number 1 in terms of installed capacity, and PV is number 2. You can see 651 and 633. This is the 31st December 2019 data. And this is the profile of wind installed capacity, both the world as well as India. There was a time around 6 years and before, wind was growing at a growth rate of annual rate of more than 25%, but it is now come down to less than I think 17% or so. Installed capacity of wind as on 31st of December, that was 37 gigawatt. Now it is more or less about 38.5. Now wind has got 2 components. Majority of the wind farms are located onshore, that is ground-based system. But there are wind farms located offshore also. Of course, in our country, as of now, we don't have any offshore wind farm. The first offshore wind farm is going to be commissioned next year. 5 gigawatt system is going to come in Gujarat area. But in the European countries, offshore wind is very high. I mean, share of offshore is very high, especially that UK, Denmark, Ireland area, because they get a very strong end. As because they are close to the North Pole. Whereas the countries which are located in the equator, wind potential is relatively less as compared to the equator area. Now, this is the solar PV status world as well as the country, our country, that is 633 world and 33.7. Again, this is 31st of December 2019. Right now, it is almost 36 gigawatt in our country. I will show you the data. Now, this is the installed generating capacity of our country. The latest data available in CEA site, because number data is not yet updated in the CEA site. So it is, there will not be much change in the data. So you can notice that our installed capacity, grid connected installed capacity is about 373 gigawatt. And we also have about 60 gigawatt, close to 60 gigawatt captive power plants as well. So put together these two, you can see our installed capacity is at least 430 gigawatt. Because this data shows generating units more than 1 megawatt, because there are lot of generating installations with the capacity less than 1 megawatt. That is not reflected in this data. So what I mean to say is our installed capacity is very high, around 430 plus, and we are number 3 in the world in terms of the generator or powers generating installed capacity. And out of that, about 89, closely about 90 gigawatt is contributed by the renewables. And you can notice that wind is number 1, solar is number 2. So wind is contributing 38 and solar PV 36. This is, please remember, this is 31st October. So last 1 month, during the last 30 days, it must have increased marginally. So it must be now around 90 gigawatt. So if you see the share of renewables in the total generating capacity of our country, it is close to 24%. And please remember our target, renewable target in total installed capacity by 2030 is 40%. So we have already achieved nearly 60%. So it is easy for us to meet that target. But our short-term target, it will be difficult because we have 2 targets. One is short-term, that is ending 2022, that is 175 gigawatt. Out of that, 100 is going to come from solar and 60 is going to come from wind. And remaining 15 gigawatt is going to come from small system, biomass based, etc. So where do we stand as per this target? This is the current status of the renewables in our country. Our target of solar PV for 2022 is 100, whereas we have just reached around 36. It's very difficult for us to meet that target. And in terms of wind installed capacity, we have crossed nearly 60-65%, but still it is very difficult. Whereas the other biomass, small hydro, etc., we have more or less reached that target. So these two are the pain points, that is solar PV and wind are the pain points. And time to time, Minister of Power make statement that recently some news article, in a news article, some interview has come in which somebody has asked about this target. So he was of the opinion that we may not be able to meet the target by solar and wind, but put all together, we may be able. But now 2020 is over, 1.5 years left, not even 1.5 years, 1 year and 4 months left. It is very difficult to meet that target. But we have the long target, that is by 2030-32. We expect that our installed capacity is going to be 800 gigawatt. Out of that, 40%, that is nearly 320 gigawatt, is going to come from renewable. So it may be possible for us to meet that target because currently we are already reached 24% that penetration level of renewables. Now let us see 2 technologies more in detail. One is the wind energy conversion system. Second is the solar PV system. Now, time to time, Government of India, under Government of India, that MNRE, again under MNRE, there is a dedicated department for the wind energy. That is, initially they were used to called as Center for Wind Energy Technology, CWET. CWET. but it has been renamed as the National Institute of Wind Energy. This is a Chennai-based agency, and they published this wind profile map of our country. And please note that when you are talking about the wind potential, always you have to consider the height at which you are measuring the wind speed. This is basically for the 100 meter. You can actually see when you go through the MNRE site, you can see this wind potential map for 50 meter, 80 meter, etc. Now the significance of this 80 meter or 100 meter is, as you know that with increasing elevation height, average wind speed increases, and thereby the wind energy potential also increases. So this curve shows that average wind, that green color, within about 5.4 meter. It is very low in terms of energy capacity is concerned. Wind speed below 5 meter per second is not a very good wind. And unfortunately, in our country, average wind speed is in the range of 5.5 to 6.5 or at the most 7 meter per second. So that way we are not good in terms of wind installed capacity. Only corrective action we can take for getting maximum wind potential is increase the height of the wind turbine. But again, there are technological challenges, because in our country as of now, the largest or tallest wind turbine is of around 120 meters, and the world it is around 140 meters. Now, at a different hub height means the height of the wind turbine center of axis from the ground. It is something like this. This is your wind turbine. So this height, this is the hub height. So earlier, MNRE published data for 50 meters, and about 10 years back it was 50. Then they have published 80 meter, and currently it is 100 meter. Now you see that potential, wind energy potential is equivalent to around 49 gigawatt at 50, whereas at 100 it is 300. And if you can increase the wind turbine height to 120 meter, then we have the potential of more than 3000 gigawatt. And the tallest wind turbine currently running in this planet is 140 meter. And 160 class wind turbines are going to be hitting the market in the next year. So that way, our potential, wind potential is enormous, because so far they have evaluated the potential only up to 120 meters. Beyond that is yet to be evaluated. But maybe within 1 or 2 years, we may get some information about 140 class or 150 class. So accordingly, we can get some idea. This is, please remember, this is onshore data. We also have offshore, because the advantage with our country is we have nearly 7,600 kilometers of coastal area, and especially our western part as well as the southern part, we have tremendous wind potential, especially that Kanyakumari area, Pondicherry, Rameshwaram area, Gujarat area, etc. are high wind areas. Some of you must have visited Kanyakumari, and you must have felt that heavy wind. So those are some of the locations where we have good potential for offshore also. But relatively, our eastern potential, that is Orissa, West Bengal, Andaman Nicobar, that location, wind potential is not very strong. Of course, wind is there, but it is not very strong as compared to south and west. Now, fundamentally, there are two technologies used in the wind turbines, that is vertical axis and the horizontal axis. Vertical axis wind turbines are one of the oldest type. This is the oldest one. And thereafter the horizontal. And recently a new concept has emerged in the wind turbine technology, that is basically a floating type airborne wind turbine. So we will start with the vertical axis. Vertical axis wind turbine is not very popular nowadays. Now, this is the graphical representation of the wind turbine, vertical axis. There are 2 or 3 blades. You can see that photograph. 2 blades are there. This is basically the blade where the energy conversion happens, and it is transmitted into the generator through a complex gear system. Now, the drawback about this particular design is height of that structure, it is limited because it is a freestanding structure and it has to rotate. So there are mechanical related stability issues. Plus, the generator is located in the ground. Gearbox is also located in the ground, so it makes a lot of noise. People staying near, especially this European people, those who are staying near these wind farms are not very happy about this wind turbine. It is not very economical. It is very polluting in terms of noise, and it is not. Its capacity is also limited because of the height limitation. The most popular wind turbine commercially used nowadays is the horizontal axis, that too 3-blade system. This is the typical cross-sectional representation of a 3-blade wind turbine. The most important component of the wind turbine is the blade. It is aerodynamically shaped aerofoil. That is, the shape is called as aerofoil. It is something like our aircraft wing. 2, 3, or 4 blades will be there. Standard is 3, and three blades are connected to a hub. That the center one is called a hub. This is the hub, and it is connected to a low-speed shaft. Then there is a gear coupling, and then comes a high-speed shaft. Then comes the generator. Now, wind turbines are very slow speed rotating machines. And the largest wind turbine currently running, that is 164 meter diameter, its nominal speed is around 6 to 8 RPM. Now the question is, if your turbine rotates at a speed of say 15 RPM or 7.5 RPM, or for that matter, let us consider that 30 RPM. Suppose say your turbine speed is 30 RPM. Now with the 30 RPM, how can we generate 50 Hertz signal? Because our grid is designed for 50 Hertz, or for that matter, if it is a US, it is 60 Hertz system. So how you can generate a 50 or 60 Hertz power supply with a 30 RPM prime mover? It's very difficult. Of course, we can generate, you know, that N equal to 120 F by P. So with a 30 RPM turbine, we need a generator with a 200 number of poles. 200 number of poles, a generator with a 200 number of poles standing at a height of about 100 to 120 meters from the ground. It is practically very difficult. Of course, that is a very high speed. In NTPC, we have 2 megawatt wind turbine. Its speed is just 15 RPM. And if it is 15 RPM for generating 50 Hertz, we need 400 number of poles. It is practically impossible to make a generator with a 400 number of poles standing at a height of about 120. So, to reduce the size of the generator, the easiest method is to put a gearbox, and that is why almost 80 to 90% of the commercially running wind turbines have gearbox. Of course, you can have gearless wind turbines as well, but it will be very bulky. So there will be a gearbox, and the gearbox is one of the most critical component of this system because failure rate is much higher. Then comes a small dia generator shaft. Typically, the diameter of the turbine shaft is around 1 meter, low speed shaft, and generator shaft diameter is around 18 to 22 centimeters. It is very small, just like what I can say, the small turbine shaft. Now, all these major components like slow speed shaft, gearbox, and high speed shaft, generator, etc., are enclosed in a container that is known as nacelle. So, what we see from outside is only that X-shaped container, that is the nacelle. Of course, it is very huge. Helicopters can land over that. 5 megawatt wind turbine or the top of that nacelle, there is a helipad. So, you can imagine the size. There is a safety mechanism provided in the high-speed shaft. That is the disc brake, just like our two-wheelers and four-wheelers. Please note that the disc brake is provided in the high-speed shaft, not in the low-speed shaft. Reason being, torque generated will be very high. Then over the top of that nacelle in the rear side, you can see the transducers for sensing the wind speed as well as the wind direction. Because wind speed sensing is very important. Reason is, the wind must be hitting the wind turbine blade in a particular optimum angle, that is known as the angle of attack. Then only that the blade can capture that energy and it can provide that lifting force. that force which is responsible for rotation of the blade is the lifting force. Of course, there is drag force also, but horizontal axis wind turbine normally uses the lift force for rotation of the shaft. So that efficiency will be optimum only when the wind is hitting the blade in a particular angle. And you cannot imagine that wind will be always hitting the blade in that optimum angle, because wind direction will continuously change, randomly change. So we need to see the direction of the wind, and we also need the wind speed. There are two reasons for that. In our thermal power plant, our fuel, you know that it is coal. Suppose say it is 100 ton coal is required for generating, suppose say 200 megawatt. So we know that rough figure, but still we calculate, we continuously monitor and chemically analyze, and we have online transducers also to measure the calorific value. Why we need to measure the calorific value? Does it mean that without knowing the calorific value, you cannot generate steam in the boiler? It is not that way, because it is mainly in thermal power plant, it is actually cost. Efficiency means cost. So if you get a good quality coal, with a lesser amount, you can generate the designated or that optimum output. And if the coal quality is poor, naturally we have to pay more. Same is the case with the wind turbine also, because wind turbine is designed for a particular wind speed, say 10 meter per second, 12 meter per second, or 13 meter per second. If the wind speed is low, it will generate less. That is one thing. There is one more important aspect why we need to measure the wind speed. That is for the controllability. Because for controlling the wind speed, wind turbine speed, we need to know the wind speed also. Because there is a correlation between the power output, wind speed, and the rotor speed of the machine. We will see that one in the subsequent slides. So these two mechanisms are very important. Of course, it may not be in conventional form nowadays. Everything is electronics and radio signal frequency based. So you may not be physically seeing an anemometer, but functionally it will be there. Now, suppose a wind direction has changed. Initially, suppose a wind was coming from the left-hand side and striking the blade, but direction has changed. So in that case, through this sensing mechanism, signal will go to a controller that is basically called the yaw controller, and it will tilt the facing of the wind turbine so that wind turbine will be always facing the optimum wind, and you will be getting the optimum output. Now the question is, wind speed will never be constant, even though your wind turbine is designed for a particular wind speed of say 12 meters per second. But you cannot expect that the wind speed will be always 12 meters per second. It will be going up and down. So that means rotational speed will also vary. And a generator, rotational speed changes means its frequency will vary. And what we need is 50 hertz. So because of the fluctuating wind, because of that varying frequency output, we need a converter. That is AC to DC to AC converter, because actually it is back-to-back conversion. Because this is AC signal, suppose this is 10 hertz. So naturally you cannot connect that 10 hertz with the power grid. So first this 10 hertz AC will be converted into DC. Then that DC will be converted back into 50 hertz AC. So this converter will generate 50 hertz. Now where you are going to connect it? At 11 kV for 15 volt or 33 kV. So depending upon that voltage level at which you are going to connect. So there you require a matching transformer. So the individual components associated with the wind energy conversion system includes the aerodynamically shaped blade. The most critical and important component of the wind turbine is the blade. Then that rotational speed of the wind turbine blades will be very low. So you need a step-up gear for matching the high-speed generator. Because if you make a generator for low-speed application, then it will be very large in size. So by increasing the speed, generator will become extremely small and compact. Then we need a frequency converter, AC to DC to AC, for getting 50 hertz. Then there is a matching transformer for the grid connectivity. Out of this, the aerodynamics of the wind turbine is the most critical component, because the efficiency of the wind turbine is in fact controlled or limited by that aerodynamic. Because all the other components like a gearbox, typical efficiency is 98%. generator, typical efficiency 98-99%, converter 96 to 98%, transformer 98-99%. Then what is the problem? Problem is here, this system. Here the efficiency will be in the range of 45 to maybe 40 to 45 at the most 50, because the theoretical maximum efficiency limit of the wind turbine is 59.3%. That is known as Betz limit. So no wind turbine in this planet can have efficiency more than 59.3%. Now a little bit about the mathematics about the wind turbine. The power output of the wind turbine is represented as half rho AU cube Cp, where A is rho is the density, A is the sweep area. Sweep area means when wind turbine rotates, it covers that area. Then U, that is the wind speed, and Cp. Cp is basically the performance coefficient or efficiency coefficient. Now what you can observe here is wind turbine output is directly proportional to density. What does it mean? It means density will be affected by ambient conditions like temperature. So daytime and nighttime there will be difference in the density. That means performance of the wind turbine will not be uniform during night and daytime. Second, location. Location means if it is very close to sea area, naturally that air will be more denser. But if it is say located in a hilly area, it will be very lighter. So location also same wind turbine. Suppose say you have a 2 megawatt wind turbine located. One is located in coastal area, one is located in a hilly area. There will be difference in terms of density. Of course, hilly area your wind will be very high. Speed of wind will be very high. So naturally that will be compensated. Then comes the size of the rotor. Because it is proportional, the power output is proportional to pi r square. So it is square of the radius. And this is the only parameter the designer can change, because all other parameters are governed by the ambient. Then of course the wind speed, cube of the wind speed, naturally that is not in our hand. If higher the wind speed, you will get a better output for the same size of the wind turbine blade. And of course the design, that is the profile of the wind turbine blade, that is basically the aerodynamic shape, aerofoil shape. And if you plot this equation mathematically between rotor speed and the power output, for each wind speed you can see different curve. And please pay a little attention in this curve, that for a particular wind speed, for example, say 14 meter per second wind speed, power output will be maximum at point A. What is the significance of that point A? You have a particular rotor speed. That means for a particular wind speed, say 14 meter per second, the power output will be maximum only at a particular rotor speed. That particular point at which the power output is optimum for a particular wind speed, that point is known as maximum power point. And we can get a maximum power point for every wind speed. You can calculate it mathematically. And if you plot all these MPPs, maximum power points, you will get that red line. And that line is known as the maximum power point tracking. It's a very important concept in case of wind and solar PV systems. Maximum power point tracking. And that MPPT curve, that red curve, is typically given in the data sheet. When we purchase the wind turbine, this is the curve they give in the data sheet. Now here, x-axis is the wind speed and y-axis is the power output of the wind turbine. And you can notice that there is a minimum wind speed required for the wind turbine to start generating power. And that wind speed is known as cut-in wind speed. Typically, it varies between 3 to 5 meters per second. In European countries, average wind speed is very high. Typically, cut-in wind speed will be in the range of 5 meters per second. That means when the wind speed exceeds 5 meters per second, then only that wind turbine generator start generating power. Whereas in our country, average wind speed is very low, typically 4.5 to 6.5. So naturally, you cannot design a wind turbine with 5 meters per second cut-in wind speed. You will be wasting a lot of energy. So normally, in our country, the cut-in wind speed is typically 3 or 2.5 or 3.5 meter, typically 3 meters per. Because in NTPC, we have two different makes of wind turbine. cut-in wind speed is 3 meters per second. And after 3 meters per second, with the increase in wind speed, wind turbine output increases. And by about 11 to 12 meters per second, it reaches its full capacity. For example, say 2 megawatt output. This is basically the data sheet of NTPC wind turbine, 2 megawatt output. And its nominal speed or rated speed is, wind speed is 11 meters per second. That means at 11 meters per second wind speed, NTPC wind turbine reaches its full capacity of 2 megawatt. Now, wind speed, we cannot expect that wind speed will go only up to 11 meters per second. The speed may go up, or it may remain same, or it may come down. If the wind speed increases, as per that equation, the equation which we have seen in the previous slide, power output of the wind turbine must increase, but that will not happen. Wind turbines are designed for its maximum capacity at the nominal wind speed. After that, when the wind speed increases, wind turbine output will not increase. That is mainly for safety reasons. And by about 20 to 25 meters per second, wind will become very energetic, like a storm or turbulent wind, cyclone, etc. Under that condition, we cannot let the wind turbine to generate power. Safety is more important under that condition. So wind turbines will be taken out of service. For that, safety brakes are there, disc brakes are there. Then blade profile is also made in such a way that beyond certain speed, typically say 20-22 meters per second wind speed, that there will be some stalling effect, and wind turbine blade can also be tilted 180 degrees, so that aerodynamic efficiency will become extremely poor. So wind turbine will come out of service. Now, typical capacity factor. Capacity factor is basically the planned load factor. It is the power energy produced divided by power into time. Suppose say if you consider a 24-hour duration, then how much is the actual energy produced divided by how much it would have produced if it had operated at its full capacity. So the actual energy produced divided by the theoretical maximum energy could have generated. That ratio is the capacity factor, or in thermal power plants or normal power sector, we call it a planned load factor. So that figure is very low in case of wind turbine, especially in our country. The highest figure may be about 40-45, maybe in the European countries, that too offshore. In India, maybe around the 25-30%, up to 30% is okay. But beyond that, it is very difficult. Of course, there are few locations where the wind is very strong. This is the photograph of the largest wind turbine currently running. It is basically Vestas. Vestas is the #1 topper in terms of the installed capacity and design. It's a Denmark company. There is something called a Danish concept in wind turbines. So it is a 9.5 megawatt machine, and the next largest machine going to hit the market is GE, General Electric. That is 12 megawatt, and that is going to be 180 meter blade diameter. This particular meter blade diameter is 164. That end to end. I will show you the curve. This wind turbine reaches its full capacity at about 13 meters per second, and you see that rated speed, rotor speed is very slow speed machine, because there is an inverse relationship in case of wind turbine. That is, with the increasing capacity of the wind turbine, its speed of rotation reduces because of the centrifugal forces. Because you know that centrifugal force is that 2 pi r into rotational speed. So with the increasing diameter, the tip speed, the speed felt at the tip of that rotor will be extremely high. And there is a correlation between the tip speed and the sound velocity. So in order to maintain that gap, always the rotational speed will be reduced when the diameter increases. For example, in case of, you can compare this with steam turbine generators and hydro turbine generators. Steam and gas turbine driven generators are very compact. Small in diameter, hardly 1 meter to 1.2 meter to 1.335. For example, a typical 660 megawatt machine in NTPC, generator rotor diameter is 1.34 centimeter. I mean 1 meter, 34 centimeter. That's it. But if you consider a hydro machine, maybe a 100 or 200 megawatt hydro machine, diameter of that machine may vary from 8 meter to 16 meter, because speed of rotation will be low. Whereas you know that gas turbines and steam turbine rotational speed in our country maximum is 3000, whereas in a 60 hertz American system it is 3600. Now, if you see the efficiency of various components associated in the wind turbine, wind energy conversion system, already I have told you, it is that a blade, aerodynamically shaped blade, which is the most critical component of a wind turbine, because other components like a gearbox, generator, converters, etc., all are very good. So, designers' main concentration is how to improve this aerodynamic efficiency. Even 1% improvement in the efficiency means drastic change in the power output. And the most critical component, which is failure prone, that is the gearbox, and it is very heavy also. So there are wind turbine designs currently available without gearbox also, but those are very expensive machine. Now these are the different working profile of the wind turbine. You can see this here. This is basically the yaw control. That middle one is changing the facing of the wind turbine whenever the wind direction changes. This is through that yaw control. And the third one, rightmost side, that is basically the pitch control. Because for optimum capturing of the energy from the incoming wind, wind energy is basically the kinetic energy. So for capturing the kinetic energy of the incoming air mass, that is a wind, there is an optimum angle of attack required. So whenever the wind direction changes, this wind turbine blade tilting can change. We use this particular principle in our thermal power plant fans, because for controlling the loading on the fans, we can tilt it. That is blade pitch control. So this is the yaw control, and this is the pitch control. Pitch control is basically for controlling the rotor speed, whereas yaw control is for changing the facing of the wind turbine aligned with the wind direction. Now, classification of the wind turbine, we have already seen horizontal axis and vertical axis. Then, based on the number of blades, we can classify the wind turbines as single blade, double blade, and 3 blade, or even 4 blade or large number of blade system. Because during that early 1990s, when this wind turbine started hitting the market, different designers and manufacturers have come with a different concept. Because for reducing the cost, single blade system, the advantage is, since it uses only one blade, naturally it will be very cheap, less expensive. And not only that, it can operate at a relatively higher speed also. Normally where we apply this one, they use this one. Location where the wind speed is extremely high, maybe some hilltop areas where we are not concerned about the efficiency, we need some power, that's it. But it is not a balanced system and it is not an efficient system. So it is commercially not used. Then comes the double blade system. Double blade system is somewhat better in terms of efficiency as compared to the single blade, but it is relatively more expensive as compared to single blade system. And you can see that a peculiar problem faced by this double blade wind turbine, because when the blade becomes perpendicular to the tower, because your tower is here, and your blade is, suppose it is something like this. So one portion of the blade is actually blocked by the tower, whereas the top side blade is free to move. So there will be an unbalancing force acting on that results into that particular type of issue. And there are reports that double blade wind turbine bearing failure rate is relatively high because of that problem. But it is a balanced system, of course, but it is not the best design in terms of efficiency. Then comes the best design, that is the 3 blade system, because with the increasing number of blades, speed will come down. So this is the low speed machine. So naturally, the noise produced by this machine is the minimum. So people are not very unhappy about the wind turbine noise. Whereas single blade system, naturally, it will be very highly noisy. So people will not like it. And it is more balanced, and that the second double blade system, that unbalancing problem will not be occurring, because blades will never be, 2 blades will never come in parallel with the tower, only 1 blade at a time. So unbalancing force will not be much in this case. So it is said that these 3 blade systems are nearly about 10% more efficient compared to the single blade system. Now the generators, used in case of wind turbine, because wind turbine is a prime mover, and you know that for converting mechanical energy to electrical energy using the electromagnetic induction principle devised by Michael Faraday, we need a generator. There are two kinds of generators, AC and DC. Of course, nowadays DC generators are not used, but during 1920s, there were DC generators used in case of wind turbine, but DC generators are no more popular. So it is AC generator. Under AC generator, there are two technologies. One is the synchronous machine, second is the synchronous machine. In synchronous machine, magnetic field is uniform because we are using DC excitation, whereas in a synchronous machine, magnetic field is created by varying polarity. So AC. So the magnetic field will not be unipolarity always. So there are plus points and minus points. In terms of controllability, synchronous machine is better because it can independently vary its output megawatt and megawatt, whereas in a asynchronous machine, controllability is much less, but it is less expensive. Now thermal power, I mean, bulk commercial electricity is normally produced by synchronous machine, because we have already seen that commercial about 75 to 80% of the commercial electricity is generated by turbines. Turbines mean gas turbines, steam turbine, hydro turbine, of course, that is not coming under this category. So synchronous machine driven by thermal prime mover, that is steam and gas turbine, usually uses this technology invented by Nikola Tesla. But asynchronous machine, it is basically very cheap, relatively very cheap, and rough and tough machine, and the longevity is very high, and maintenance problems are relatively less as compared to the synchronous machine. Now, renewable energy systems based on wind energy, small hydro, and wave energy, etc., are mainly using the asynchronous generators, because for capturing energy from varying resource like wind or small hydro, where actually you have to continuously change the speed. But if you use a synchronous machine, we always need to maintain constant speed. And in case of renewable energy, maintaining constant speed means efficiency will not be optimal. So that is one reason why asynchronous machines are commonly used in case of renewables. This is the typical operating curve of a asynchronous machine, the so-called induction machine. Upper one is the motoring mode, and bottom one is the lowering mode, because asynchronous machine can operate either below synchronous speed if it is in motoring mode, and above synchronous speed if it is in generating mode. And typically these machines are called constant speed machines. Why? Because speed will not change much when the frequency changes, because the range we operate, that is actually very narrow. So usually maybe about 2% slip at the most, or 1% slip. So not much change, I mean variation in the wind rotor speed. But that is not an economical way of operating the machine, because for capturing optimum energy from the wind, what we need is a variable speed generator in place of a constant speed machine. But if you consider the cost, asynchronous machine, constant speed machines are very cheap, relatively very cheap, but with less flexibility, controllability. So actually, it is a techno-economical balancing act. Now, there are nearly about 12 different technologies currently available under the wind turbines. Of course, here we will just briefly touch upon about the 4 different technologies: Class A, or Type A, Type B, etc. Type A wind turbine is basically fixed speed, means no controllability in wind, rotor speed. Remaining all are having limited to maximum or full range of controllability. So naturally, complexity and cost will also vary. Rotors of the generators uses 2 technology. One is the cage rotor, squirrel cage rotor. Naturally, you cannot control the speed. Second one is the wound rotor. So all the fixed speed wind turbines uses cage rotor design, whereas variable speed wind turbines uses wound rotor design. And this is the first or the simplest wind turbine. There is no speed variability, controllability. You just purchase an induction motor. Induction motors will operate only below synchronous speed, because there will be a slip of 1% or 2%. The same machine, if you operate above synchronous speed, it will act as a generator. But problem is, When you connect an induction motor with a wind turbine and try to operate as a generator, it will not generate electricity. Why? Because excitation energy is not there. And that is the reason we have to provide excitation. If you use an induction machine as a generator, it could be a transformer, it could be a capacitor, or maybe anything. Maybe even a battery is sufficient. Some energy storage is required for providing the initial excitation. Now, we don't have much controls in this machine. It is the simplest one, but it is not the efficient one. That if you want efficient operation or efficient power output from the wind turbine, naturally, we have to control the rotor speed with respect to the variations in the wind speed. And for that, you need sensors for the wind speed, sensors for the rotor speed, and controllers, complex controllers. Then we can change the wind speed and rotor speed and optimize the output. Now here, wound rotors are used, and the output of the wound rotor is actually rectified, and dropping resistance is provided for changing the rotor current, and accordingly we can control the rotor speed and get the efficiency. But control range is much less, not a very good design. So commercial use of this one is also not very good. The best wind turbine in terms of cost and controllability and performance, it is this one, doubly fed induction generators. Here it is also a wound rotor machine because rotor windings are available, terminals are available for manipulation. Stator is directly connected to the grid through a transformer or directly connected without transformer also, depending upon the design. And a rotor circuit is also grid connected through a back-to-back converter. So you have AC to DC, then DC link, and DC to AC. So this rotor is basic. This converter is used for controlling the rotor speed. Now the rotor capacity, rotor is using power electronic converters, and the capacity of this rotor electronic converters is in the range of about 30%. That means this machine can supply megawatt through the stator terminals, and when this machine is operating above synchronous speed, it can also generate megawatt through the rotor circuit when it is operating above the synchronous speed. So this back-to-back converter has got a flexibility. It can take megawatt from the grid, or it can supply megawatt to the grid. So normal range is about 30%. That means the speed control range of this machine is in the range of 66% to 133%. That means total about 66% of speed you can control, and it is very good. But that is not the perfect one or the ideal one. It is commercially, it is very popular. About 75 to 80% of the wind turbine commercially running uses this doubly fed induction generator principle. Whereas if you are very particular about the efficiency, if you want to capture the entire energy in an optimum manner, that means you have to vary the rotor speed during the entire range from the cut-in wind speed to the cut-out wind speed. And for that matter, you need a power electronic converters in the stator circuit, and the entire stator power is passing through that. So that means this is the most expensive one. Now coming to the solar PV system. Solar PV systems are available in different design. The energy what we get as solar energy or wind energy, etc., everything is coming from the sun only, and the distance matters. After traveling, the distance between sun and earth is about 149.5 billion kilometers. And there is an inverse square law as far as energy is concerned. As the energy travels towards earth from sun, its intensity comes down, and by the time it reaches the earth's surface, earth is having a surface of 100 kilometers. By the time it reaches the earth's surface, it will become about 1,368, and plus minus there is a deviation of 3.5. Yes. Now, what is this solar energy? Solar energy is basically the entire electromagnetic spectrum emitted from the sun. It is also known as the black body radiation in mechanical thermodynamics. It consists of energy spectrum in the left hand side, that is high frequency, and right hand side it is low frequency, and in between, middle, we have a spectrum band of 380 to 720 nanometers. That is the so-called visual spectrum. Now, the so-called photovoltaic technology captures energy from the visual spectrum, that is 380 to 720 nanometers. But unfortunately, we have a lot of energy right hand side of the visual spectrum, lot of energy in the left hand side of the visual spectrum. Those energy cannot be usually captured by the typical solar cell. Suppose it is a silicon solar cell, it cannot capture, and that is why a lot of research is currently happening, so that the bandwidth of the solar cell will be further stretched towards left hand side as well as right hand side. But right hand side is basically thermal area. Infrared domain basically temperature, high temperature zone. So performance of the PV will not be very good towards right hand side. Now the energy which is coming from the sun after passing through the 100-kilometer thickness, because we have seen that once sunlight reaches the Earth's surface, Earth is having a thickness of 100 kilometers. So once the light reaches here, solar energy, it will become 1368 plus minus 3.5% watt per meter square. This is basically the power density. Then as the light passes through this 100-kilometer thick, there will be a lot of disturbances, because energy absorbing foreign material will be there. And by the time it reaches the ground level, that is 0 meter level, it will become just 1000 watt per meter square. And that is the reason our solar cell or modules are designed for 1000 watt per meter square, the so-called SPEC, standard test condition. So these are various losses, because the atmosphere consists of many things, like dust particles, smoke, then carbon soot from vehicle, then vapor particles, cement particles, smoke from power plants, etc. Nearly 28% of the energy is lost. You can see that. Now that radiation, what we are getting from sun, the so-called visual spectrum meteor, it has got different colors. And what is the meaning of this different color, different energy level? And a single energy conversion system cannot capture all the energy efficiently from that spectrum. So this solar, for capturing or converting the energy from the solar spectrum, we need different conversion mechanism. This ultraviolet and visual spectrum, nearly about 56% of the total energy in the solar spectrum is converted using the photovoltaic technology, the PV technology. Whereas right hand side of visual spectrum, that is basically infrared, and further right hand side, that is basically coming under the thermal technology. So there are two fundamental technologies under the solar energy. One is called the solar photovoltaics, second is called the solar thermal. Currently, solar thermal is very expensive. In fact, before the solar PV becomes so popular, about 10 years back, solar thermal was getting a lot of attention, because relative cost of solar thermal was very less 10 years back. But now solar PV cost has come down like anything. Now nobody talks about the solar thermal except researchers, those who are involved in the research. So let us now switch over to the solar PV. Solar PV is basically capturing of the incoming energy from the incoming photon. Photon is, as per definition, photon is massless energy carrier, travels at the speed of 3 into 2.98 into 10 power 8 meter per second. And normally we consider the same speed for the electrons as well. That is why we say that electricity travels at the same speed as that of light. But there is a difference, because light is the fastest physical system that I believe, because there are few other things. Somewhere I have read that which can travel faster than light. Maybe there, but as of now, from practical aspect, I consider light is the fastest moving physical system. Electricity cannot travel at that same speed. Of course, for short distance from, suppose, if you consider only Earth diameter, from one part of the Earth to the other part 180-degree apart, that distance is relatively less as compared to the distance between Earth and the Sun or Earth and the Moon. So there we will not find much difference, relative speed difference between the electricity speed and the light speed. But if you compare the speed, electron speed and photon speed between Earth and the Moon or Earth and Sun, there you can feel it. Now here, then, when these photons strike a PV material, semiconductor material, electrons will be dislocated from low energy band to high energy band, that is valence band to the conduction band. And thereby we can get a current flow by tapping that electron through external circuit. And that mechanism that a photovoltaic principle can be explained using like this, because you know from the atomic physics that any material can be represented using the band theory. So electrons usually remain in different bands of with a different energy level. Valence band is basically a closed system or a closed band. Electrons are not free to move. Now, when photons strike, incoming photons strike electrons in that valence band, it will be dislocated, overcoming the band gap. There is a band gap, electrons cannot remain in the band gap. So by lifting this electron from the valence band, by hitting it, then it will be taken to the conduction band, and the conduction band of electrons available means it is free to move around, and it can be tapped through the external circuit also. So this is the fundamental basic representation of the solar PV cell. It consists of semiconductor P layer and N layer, and when you combine these two, it will act as a p-n junction diode, our basic fundamental electronic system. And thickness of this is cell building block, fundamental building block is known as cell, and thickness of a cell is typically in the range of 160 to 240 micron. Typically, in NTPC, typical thickness is around 200 micron or 0.2 millimeters. And it is a current source in parallel with the diode, because p-n junction is a diode, and when it is subjected to photons, it will generate current. That is why this is the electrical representation of the solar PV. Open circuit voltage of a typical silicon-based PV cell will be around 0.6. When it is loaded, it will become about 0.5. And the current, of course, depending upon the thickness and dimension of the cell, current may be 8 ampere, 10 ampere, 6 ampere. It is not constant, but voltage is always constant, whether it is a 1 mm size or 1 centimeter size or 10 centimeter size. Now, this is the relationship of physics of the solar PV cell. Power output of the or current generated in the solar cell is function of the solar radiation. It is represented as capital G, and it is also a function of temperature as well as wind speed. There are certain correlation. Power output of the cell is directly proportional to solar radiation. It is inversely proportional to the temperature. There is a inverse relationship between power output of the solar cell and its temperature. That means temperature with increasing temperature, power output will come down. Now there is another relationship, that is the wind speed. Because temperature and wind speed, there is a direct correlation. When wind speed increases, temperature will come down, and when temperature comes down, solar PV output will increase. Solar PV output increases because the losses will come down. It is not that radiation level is changing. For the same solar radiation striking a PV cell at a particular ambient temperature, output will be higher if wind speed is more, or if the wind speed is low, there will be less output. This you can feel during, especially during peak summer period, June-July period, you can feel this effect. Now, typical cell output is 0.5 volt when it is loaded. Current may be 9 ampere or 8 ampere. So it is not a practical device to power a device. Even if you consider a cell phone, for charging that cell phone battery, you need typically about 10 watt power. A single cell will not be able to provide that much. So many cells will be connected in series to form a module. So what we get from the market is basically a solar module. It comes in multiples of 12. That means you can find modules of 36, 48, 60, 72, 84, 96 like that. It is actually that 12 has come because of the lead acid battery voltage. So this is the typical data sheet of a PV module. What we have in our NTPC, it's about a 295 watt peak. Normally PV module output is represented by watt peak. Watt, W stands for James Watt's watt, P stands for peak, that is basically DC. It simply says that the output is DC, that's it. And it is a 72 cell module. Voltages and currents are given. There are 3 parameters shown here. I will explain these parameters more in detail, because when you are going to purchase a PV module, whether it is a industry purpose or a commercial purpose or even our domestic purpose, we have to be a little careful about those 3 parameters. That is basically the temperature coefficient, means the performance of the module with increase in the temperature. This is the typical current voltage characteristic. X-axis is voltage and y-axis is current. You can see that when the radiation level changes, that is the radiation, sun radiation, solar radiation striking on the module changes, the current level changes drastically. Whereas changes in the open circuit voltage is not much noticeable. So voltage is not the parameter to judge the performance of a PV cell, just like our car batteries. Because when you take your car battery to the roadside mechanic, he will simply check the voltage across the car battery using an ordinary bulb. And if the bulb is glowing, he will say that your battery is okay. But your battery may not be okay because you don't know what is the status of the electrolyte inside the battery. Same is the case with the PV. So never ever judge a performance of the module just by seeing the voltage. It is the current that we have to concentrate upon. Now this is the voltage and the power characteristic. This identical curve. Again, you can see that with the variations in the radiation, voltage deviation variation is not much significant, but power change in the power output with the changes in the radiation level is very significant. Here also you can notice that for a particular radiation, say 1000 watt per meter square, the power output will be maximum at a particular point. Let us call it as A. Same way for a radiation level of 100 watt per meter square, this is the power output. So point A and point B, these are the maximum power point. And if you join all these power points, maximum power point, you will get a line something like this. This is the MPPT. Same as your winter band MPPT. So these inverters which are used in case of solar PV and winter band are actually work under the MPPT condition. That is why these inverters are relatively more expensive as compared to the conventional inverter we have in our houses for our backup supply for laptop, other electronics equipments, etc. So you can clearly notice that operating at that MPP point here. This is for a particular radiation level, say 1000 watt per meter square. There are two voltages of interest. One is the open circuit voltage. For any electrical equipment, open circuit voltage is very important. Same way short circuit current. Then the voltage at the maximum power and the current at the maximum power. So these values will be given in the data sheet. And by seeing this one, you can actually evaluate the performance of the solar cell and solar module. Now at 1 kilowatt module, that is a module with of 1000 watt capacity, on an average can produce power output energy of about 4.5 to 5.5 kilowatt hour. That is average. Let us consider 5 kilowatt hour full. So if you install a 1 megawatt module, average we can expect a energy output of 5 kilowatt. Of course, this is average. Summer period it will be more, and winter period it will be less, and rainy season also it will be less. Fundamental technologies under this PV, there are fundamentally two technologies. One is the crystalline technology, second is the amorphous technology. Under crystalline, of course, you have mono and poly. They based on the technological development, and the latest one is the thin film. So efficiency decreases as you come from mono to thin film. The best efficiency is this one, and the lowest efficiency is this one. Suppose this is 20% efficient, this may be about 18% efficient, and this may be about 11% efficient. So that is the way it goes. So how to identify a solar module when you go to the market? Leftmost side and the middle one, you can observe that in between the cells, there is a white space here in case of the mono, whereas in polycrystalline it is tightly packed. There is no gap between the inter cells. This is because of the manufacturing process, because monocrystalline cells are manufactured from circular disc, whereas polycrystalline is actually manufactured using dies, rectangular shape. So in terms of space utilization, polycrystalline completely uses the space. But again, as I told you, if you see the efficiency, again, this is 20%, say this is 18%, and this is 11%. And if you consider the cost, suppose say this is 100 rupees. So in that case, this may be about 80 rupees. This may be about 60 rupees. That is the thin film is basically flexible type. So it is up to you to decide which type you want. So this is the way it goes. Normally, a typical domestic application, we may have some 5 to 10 or maybe 20 module. Usually that is called a string. But when you are going into kilowatt level, hundreds of kilowatt or megawatt level, we normally call it as a solar PV farm or array, maybe thousands. For example, if you use a 60 cell module for a 5 megawatt system, nearly 21,000 modules are required. But nowadays, 72 cell module is very standard. 96 cell modules are also available. 120 cell modules are available. I have not seen 120 cell module, but 96 up to 96 I have seen, because in our own premises we have 60, 72 and 96 cell modules. Now, grid connection of the PV system, because you can have standalone PV system, you can also have grid connected PV system. And since the output of the PV system is DC, you need a DC to AC conversion mechanism. So depending upon the size of the number of modules connected, then you can have different types of inverters. Normally, inverters are currently available for voltage levels of 800 volt, 1000 volt, and up to 1.5 kV, that is a 1500 volt DC. So for getting that much voltage, because a typical 72 cell module output to voltage will be around 36, whereas your inverter is 1 kV. So you can connect to many modules in series to get 80% of that 1 kV, that is say 800 volt. So you can connect about 18 to 19 or 20 modules in series in a string. So such modules or such inverters are known as string inverters. Now, string inverters are very popular. Even normally in our house also we have string inverter, because it is relatively less expensive and it is very simple also. But it is having a drawback. Drawback is, since all these modules are connected in series, so if any module fails, the entire string will be becoming useless. The entire power generated by the entire modules will be getting lost because of the problem with the single one, because of the series connection. So in order to overcome that, another design is available that is known as parallel inverters. Normally it is called as micro inverters. Micro inverters are parallel connections, so that if at all one particular module fails, or even a single cell of a particular module fail, nothing will happen. Only that module will be affected, but all the remaining will be available. Whereas in series connection, a single cell problem in any of the module will affect the entire module. But naturally, this technology is very expensive. Again, it is actually techno-economical balance. Then comes the megawatt level, hundreds of kilowatts or thousands of kilowatt, typical 100 megawatt or 200 megawatt systems, etc., where string inverters, extremely large in capacity, they are called as central inverters. Now with this, let us now switch over to some of the technological challenges with the grid connection, because whatever be the resource, whether it is wind related or solar related, ultimately we have to connect all these resources with the power grid. Now, grid connection will not be that simple, just like a typical 200 megawatt unit or 500 megawatt unit, because those are synchronous machines and powered by fossil-based energy system, which are their energy content is more or less uniform and not much variations expected. But when you use renewable energy like wind or solar energy for generating electricity, it is actually governed by various natural phenomena. Your day-night cycle will affect the performance. Your weather cycle will affect your performance. Your rainy season or windy season or environment Cleanliness will also affect the performance. In case of solar PV, if it is completely soil, naturally output will be very low. Location will also affect the performance. So there are many aspects we have to consider. Some of the points are shown here. Now this is the issue with the wind turbine, because the wind is a highly variable resource, and a small change in the wind output will make a drastic change in the output of the wind turbine. Reason being, wind turbine output is directly proportional to third power of the wind speed. That means a small change in the wind speed. For example, suppose say right now wind speed is say 10 meter per second, and your turbine generate or your power output is say 1 megawatt. But suppose say wind speed has now doubled. From 10 meter per second, wind speed has become 20 meter per second, and see the output of the generator now 8 megawatt. That means just doubling the wind speed has increased the output by 8 times. Now imagine that wind is changing like this, continuously going up and down. So you translate that one into a typical thermal power plant of 500 megawatt. Imagine that a typical 500 megawatt output is changing from say 10 megawatt to 100 megawatt or 200 megawatt, 500 megawatt, then again back to 400 or suddenly 450, continuously going up and down. So what will be the condition of the power grid? And what will be the condition of the equipments connected to that power grid, which is highly oscillating and fluctuating? Naturally, system stability will be affected. Equipment performance and life will also be affected, because we need a uniform power output in the system for meeting the system requirements. That will not be possible. But in wind turbine, there are certain advantages. By properly designing the wind turbine or a farm, we can actually reduce some of the impacts. For example, if you consider a single wind turbine, see the fluctuating wind and the fluctuating power output, it is highly fluctuating. But suppose say you have two wind turbines back to back. Say one wind turbine is located maybe some 500 meters below the first wind turbine, because there must be certain gap between the wind turbine. You cannot keep two wind turbine too close. Gap will be decided by the diameter of the wind turbine blade. It is typically 7 times. Suppose say you have a 100 meter wind turbine, with 100 meter diameter wind turbine, then the distance between two wind turbines will be typically about 600 to 700 meters. So if suppose two such wind turbine, so the same wind is hitting two wind turbine, so that will be delayed, because the second wind turbine will be getting the same wind after a time delay of nearly 1 minute or so. And if you take the average of these two generators, it will be much smoother. And if suppose say you have one more wind turbine like that, by increasing the number of wind turbines, then the average output of the wind turbine, that wind farm, will be more uniform as compared to a individual single wind turbine. That is one advantage. This is known as the natural smoothing of the wind turbine because of the farm. And typical wind farms are very large. The largest wind farm in our country, that is actually located in Muppandal, very near to Kanyakumari. There are more than 3,000 wind turbines there. And capacity is more than 1,500 megawatt. So if you have large number of wind turbines geographically dispersed like this, then output will be more smoother. So here, we can actually replace a thermal power plant using a wind farm if it is displayed. But if it is a concentrated wind farm, that means it is a wind farm, wind turbines are nearby, then it will be very difficult, because fluctuation level will be extremely high. Now, in case of the solar PV, location and the season. For example, summer period in Delhi, we normally get about 14 hours of sunshine, and the heat will be, or light will be, extremely energetic. Whereas during winter period, that is 21st of December, that is the shortest day, duration will be around the 10 hours. So average you can say 12 hours, because 14 and 10 hours. But issue is, in December period, not only the day duration is limited, that is shorter, but the intensity is almost 60% of the summer period. So the power generated during winter will be much less, and it is available for shorter duration. So if you compare the energy output, winter period is the worst case. So if you are going to replace your thermal units with the wind or solar PV system, of course, night time there is no sunshine, you must have adequate backup by way of energy storage system. Now, another impact about the renewable energy is the that is the shading and the cloud movements, etc., and rainy season. So during a sunshine day, peak day, and a clear sky day, output will be more or less like a bell-shaped curve. Whereas during a windy day, or sorry, rainy day and a cloud movement day, especially locations which are close to coastal area. In our country, Andaman Nicobar is a very good example for that purpose. They face a lot of problems because of the cloud movement. Their PV performance will drastically change because of heavy cloud movement. This is basically the screenshot of the output of that NTPC is having a 5 megawatt system in Andaman Nicobar. You can see that output variation during a cloudy day. See the output variation. So this will create a lot of technological challenges with the power grid because the connected synchronous machine driven by diesel engines, etc. Because Andaman Nicobar is an island. So naturally, it is powered by diesel engine. So if your wind energy system fluctuate like this, that will actually reflect on the performance of the diesel engines and their life will also be affected. Then coming to the solar PV. Solar PV is very sensitive to temperature. And when temperature increases, you know that every electronic equipment performance will deteriorate, including your laptop or mobile. When it becomes hot, you must have noticed already, performance will drastically reduce. Because efficiency and the performance is directly proportional to the temperature, or rather inversely proportional to temperature. Let us consider a practical example for a solar PV module. There is something called STC in solar PV system. STC stands for Standard Test Condition. These modules are tested under a laboratory condition keeping 25 degrees Celsius temperature. So let us imagine that our module, power, voltage, current and power, everything is 100% at a STC condition. So at a 25 degrees Celsius module temperature, your voltage is 37, let us call it 100%. Power output is a 370 watt, that let us call that is also 100%, like that. Now with the increase in temperature, one of these three parameters, that is current, that will increase slightly. I repeat, with increase in temperature in a PV system, the current generated will increase because your electron or photons, for the same photon which is striking the module, when with the increase in temperature, that low energy photons will also be capable of dislocating the electrons, and electrons will gain more momentum also. So number of electrons released will be more, accordingly current is increasing. But at the same time, when electrons will become more energetic, there will be bombardment, collision rate will also increase, that will be reflected as a fall in the output voltage. So with increase in temperature, current increases slightly, but output voltage drops at a much faster rate. And the combined effect, that is current and voltage, that is a power. And the fall in power will be much steeper. Now notice that this dP by dt, that is for a incremental change in temperature, what is the drop in the dP? These three parameters will be given in the data sheet. I have mentioned a little earlier that I will explain it separately, temperature performance coefficient. When the temperature increases, what will be the performance of the current, what will be the performance of the voltage and the current? What we are bothered is this one. For a good module, that should be as minimum as possible. So if you suppose if you have gone to the market for purchasing a PV system, you have to compare some 8-10 different modules and see which technology is having lowest dP by dt for a incremental change in temperature, which module has got the lowest reduction in the power, and that will be the best module. So accordingly, we have to decide. Then comes the shading. Shading is a big concern because today you have installed a PV system, everything was fine, there was no shading from anything. But over a period of time, some vegetation will grow and it may shade your module. And when a portion of the module is getting shaded, the entire module will be getting affected. These are some of the impact. And like that, many figures I could have shown, but because of the time limitation, I am limiting that. Now, the issue with the shading is that semiconductor, that is the bright area is your semiconductor where the energy conversion takes place from photon to electricity. But if it is getting shaded, the photon will not strike that area because there is no photon available to dislocate the electron. So naturally, that portion will not be taking part in the energy conversion. Accordingly, the current generated by the cell and module will come down. Please remember, voltage will not change much. I have already stressed that point. When shading happens, there will not be much deviation in the voltage. That's what I'm telling. Just by measuring the open circuit voltage, you cannot gauge the performance of the solar cell or module. You have to see the current or power. Then only you will get an idea. So because that shaded portion is not taking part in the energy conversion, naturally the power output will be less. And it is just a reduction in power. If that is the only case, then it is okay. But actually, it will damage that cell, and not only the cell, the entire module will be getting affected. So there are certain solutions available to reduce the impact of the schedule. One thing is, the best, easiest way is simply bypass that module. If suppose a particular cell in a particular module got shaded, and accordingly, it is getting affected, and since all the modules are getting connected in series, problem with the one cell will affect the entire string. So we don't want the healthy modules getting affected by that. So what is the easiest way? Bypass that module. So if suppose say in that particular string you have 20 modules and one module is creating a problem because of the shading. So bypass that particular module, remaining 19 will be healthy. That is using this one. But the thing is, by bypassing the entire module, you are actually reducing the output of that particular module, whereas the problem lies only with a single cell. Why do we necessarily bypass the entire module? So reduce that bypassing impact. You can actually reduce it by bypassing a substring. Substring means that U shape, that U shape, this one. So here, these particular number of module cells will be getting bypassed by using this cell. So at least the remaining cells will be available. But again, suppose say your problematic cell is this one. Suppose you have 20 cells, out of that 11, 12, 13, 14, 15th cell is having problem. But you are actually bypassing 20 cells straight away and you are losing energy. So instead of bypassing that substring, why can't we bypass only that cell? So facilities are available or technologies are available for bypassing even cell. But naturally, it will become more expensive. With increasing number of cells, your system will become more complicated. Design and manufacturing will become very complicated, and ultimately cost will be very high. But my suggestion is never ever purchase a module solar PV cell without a bypass diode. At least you must have a single bypass diode, or normally for every 20 to 24 cells, there will be one bypass diode. So if you have 60 cell module, there will be 3 cell diodes. 72 cell module, again you will have 3 diodes, bypass diode. Whereas 84 cell module, you will have 4 cells. So larger the number of bypass diode, better the safety of the PV system against the shading. Now coming to the grid connectivity. Why I have mentioned these aspects before going to the grid connectivity? Because ultimately it is the power output coming from these resources that is going to supply the consumer. And if that itself is varying, then naturally that will impact not only the grid stability, but it will also create problem with the equipment safe life. Now a typical power system is designed as a radial system. That way you generate power at one location and extend power to a remote located consumer. Power always flow in a particular direction. That is why we call it as radial direction, radial flow. But when you go for renewables, these are all distributed energy sources like wind farm, solar PV farm. Because the capacity is limited, normally small in capacity may not be large megawatt level, especially rooftop PV system where you are connecting to your 230 volt system Or if it is a three-phase system, you are connecting it to 400 or 415-volt system. So these are all LT bus switching system, loads or generators. And our distribution system, that 11 kV or 33 system, these are all passive system. Passive system means normally there will not be any generating resource connected to 33 kV system because power is coming from a big station located maybe 1,000 kilometers away from that particular substation. But because of the renewable energy connected to the low voltage grid, now your distribution system is also becoming active. Active means they are now capable of giving fault current. When fault occurs, there will be unusual behavior as compared to the original design, and your buses are not designed for that. So what are the problems we have to consider before connecting a renewable resource in the power grid? Point of coupling. What is the voltage level you are going to connect? And if suppose say that PV system fail, how much will be the voltage fluctuation we are anticipating? And all renewable resources are more or less require some power electronic converters for integration. So there will be whenever power electronics is there, there will be side effect, power quality. Then there are other capabilities and requirements. So one by one, let us see. See, there is a requirement that higher the voltage where you are connecting these resources, that will be safer. And in our country, of course, there is a notification from, I think, CRC, Jawaharlal Nehru National Solar Mission, that 5 megawatt and above systems must be connected to minimum 33 kV. Because if it is lesser than that, then if a PV system fails, then the entire system will be getting affected. But if it is connected to a higher system, like in a thermal power plant, suppose there is a 2000 megawatt station in which you have a 10 megawatt PV, that is nothing. It will not create any problem. But a 10 megawatt system is connected to a, say, 20 megawatt system, then the impact will be severe. That is exactly what is happening in Andaman Nicobar. Andaman Nicobar total installed capacity is low, but solar PV relative capacity is much higher. So if PV system fail, that will impact the DGs. So that should not happen. That is the reason why they limit these interconnecting voltage levels. Now another impact about the distribution system, because we know that the conventional distribution system, near the distribution transformer, voltage will be relatively high. And as you go away from the distribution transformer, the voltage available will be low because of the line drop. Now, when you connect, suppose you connect a PV system or wind turbine at the extreme end of the distribution transformer, then that will result into high voltages in that. Because usually, in order to take care of that voltage drop in the system, the voltage in the distribution transformer will be slightly more than the designated voltage. But because of the DG connection, there will be unwanted over voltages towards the extreme end. This happened with my house also once. So these are the aspects we have to consider. Then comes the power quality issue because of the interfacing. Because our typical thermal power plant or hydro power plant, we connect with the grid directly because these are all synchronous machine, 50 hertz machine. Whereas when you go for renewables like wind and solar PV, wind turbine for that matter, it is a rotating machine and AC generator. But unfortunately, frequency of the wind turbine generator is not 50. So we need a power electronic converter for converting that AC to DC, then DC back to 50 hertz. So that you can connect to grid. Solar PV output is DC. In any case, we need the converter. So most of the renewables are grid connected. Grid connected through the converters. And when we connect the resource through the grid, power electronic converters, then there are certain issues, because the advantage of synchronous machine is there is a natural linking between the machine and the grid. Means if something happen in the grid, machine will see that, and if something happen in the machine, grid will see that, because both are communicating continuously. Whereas in case of power electronic based interconnection, that natural link is lost. That means if something happen in the machine, your grid will not know about it, or if something happen in the grid, your machine will not understand that. So that automatic natural response will be missing. That is one thing. Second is the interface, that interference or quality related impacts because of the power electronic. because power electronic devices are non-linear devices. So they create a lot of issues like voltage variation by way of dip or interruption or swell or notch, etc. Then almost all the equipments in that electrical system, especially that electromagnetic devices, transformers, all those stuffs will be getting affected because of the high frequency third harmonic, fifth harmonic, all those unwanted signals. So there will be frequent failures of some of the equipment if you are not taking care of this harmonics. Now, one major requirement from a generator, when fault occur in the system, naturally we know that the system voltage falls. And if the voltage falls, megawatt in the system demand will be increasing. And if suppose say you have a PV or wind turbine in your house, and if under voltage happen and if you cut off that machine, it will further impact the system. So there is a requirement that when under voltage occurs in the power grid, your system should not be disconnected immediately. It should actually wait till the voltage falls to a low level. That particular feature is known as the low voltage ride through. Like that, there is high voltage ride through also, but low voltage ride through is very significant. In a synchronous machines, it is there, and whenever the voltage falls, in a typical power plants, excitation system is having a facility called the field forcing or field boosting, so that the voltage will be or the power flow from the machine will be adjusted using this field forcing. But there is no such a facility available in case of renewable resources. But here it should not disconnect immediately. It should wait till the voltage falls to set a minimal level. After that also certain time delay is there. So it is basically to support the grid. Then comes the fault level, because original system is designed for a particular current level. And when you incorporate more resources, naturally fault level will increase. Then the protection. Normally, protection devices, wherever relays are incorporated, these are all directional relays, because current flows only from one direction, from this direction. This is the direction of the normal current flow or fault current flow. Because we never anticipated any generator in the downstream. But suppose say you have incorporated a solar PV or wind turbine in the load side, naturally there is a possibility of current flowing in the other way also. So some relays, sometimes if there are directional relays, fault current in the downstream of that relay may not be reflected. That means fault may not be detected. So designer has to take care of that. So that means when you are incorporating renewables in the oldest system, it will be a tough situation. But of course, in the latest design, everything will be taken care of. Then another most significant aspect is grid support by generators by way of frequency and voltage, because once your generator is grid connected, we have two important roles. That is supporting to the frequency regulations and the voltage regulation. And for that, we have various controllers. We know that system frequency balance is maintained because of the energy balance, because the active power balance represents the frequency deviation. If the megawatt supply is more than the demand, frequency goes up. And if the megawatt demand is less than the supply, frequency comes down. And there is a device called a governor in any prime mover, and the function of the governor is to balance this mismatch between the supply and demand, megawatt, real power, active power. Likewise, we have the excitations. And purpose of the excitation, after the grid synchronization of the machine, it is actually megawatt balancing. Because sometimes voltage falls, so we increase the megawatt supply. If the voltage is high, we reduce the megawatt supply. Now, these are all inherent with the conventional system thermal units or hydro unit, because we have automatic generating governors, and we also have automatic voltage regulators. But because of the grid connection through power electronic converters, this new device or generating system may not be having this. This is the typical frequency regulation. There are various terminologies used, that is primary control, secondary control, etc. These are all available in case of typical thermal units or hydro units. And the thermal units are actually used for frequency regulation also. But these will not be available with the new systems, because there are two very important parameters which are responsible for maintaining the grid frequency. One is called the system inertia. Second is called a droop. Now, inertia means basically the kinetic energy, stored kinetic energy. That will come down with increasing in the renewable energy. So, inertia will increase, sorry, inertia will decrease, and there is another parameter that is called droop. Droop will increase. For faster response from a generating unit, droop should be lower. Lesser the droop, faster the response. But with the increasing share of renewable, droop will increase and inertia will decrease. This will actually reduce the capability, frequency and the voltage support capabilities of the units will be reduced because of this. So we have to take care of that. Now, if you just to consider the impact of increasing share of renewable, for example, I have considered a wind turbine. That red curve, frequency curve is the red one that represents without any renewable. Now, with increasing share of renewable, for a load change of this match, the frequency is falling with increasing share, that 10% wind, 20% wind and 50% wind. With the 50% wind, for the same load change, see that the deviation in the frequency. So if there is no renewable energy, with increasing in load, frequency falls from 50 to say 49 point, how much is this? 49 point, say 5. Whereas with increasing 50%, increase in share of wind turbine by 50%, frequency drop will be much steeper. So we have to overcome this one because it is bound to happen. Why it is happening? Reason already I have told you. Your inertia, stored kinetic energy of the system is actually falling. So if you are going to increase the renewable share, you have to take care of the inertia. For that, different methodologies are available, but everything is very expensive. And one method for compensating that is by way of providing storage method technologies. We have a number of storage technologies available, from conventional to ultra modern technologies. That is electrochemical batteries, then static water head, then compressed air, then flywheels, then capacitors, magnets, and even hydrogen energy can be used. And finally, even our electric vehicles can also be utilized for supporting to the grid, so that our share of renewables can be increased. For example, suppose say your office or college or university, if you have electric vehicle, instead of petrol or diesel, you can charge your car battery using a wind turbine or solar PV. And when you come back to your residence, your car battery can be connected with the grid so that it can support the grid. And during high frequency period, the same car battery can be charged from the grid also. So there is an emerging concept that is called V2G, that is vehicle to grid, and the reverse is the grid to vehicle. So there are lot of technologies which are emerging, and the question which we have raised at the beginning, that is, can we replace those thermal units with new technologies like wind and solar? So answer to that particular question is yes, but only question mark remains is when it will happen. It will take time. So what I feel is maybe by the mid of this century, in the next 20 to 30 years, we may be in a better position so that the renewable share will be much, much less. And towards the end of this century, certainly there is a possibility that our system will become more or less carbon free. So that's from my side. If there is any questions, we can take up that. Over to you, please. Organizers.
Thank you, sir. Thank you very much. So giving the lot of information about the solar grid connected system, solar panel, solar physics. So participants, anybody having any queries and any doubts, so please ask. Participants.
Thank you very much, sir. Vidyanandan, sir.
Thank you, sir. Thank you.
And presenting excellent material for our STTP participants. Thank you very much, sir. Your session is excellent. Now I request Mr. C.H. Sanjeev Kumar to present vote of thanks.
Yes. So, good afternoon, one and all. Honorable Secretary Sir, Principal Ma'am, Convener, Co-Convener, participants, and most invited guests, faculty members. My privilege to propose vote of thanks for this session on behalf of St. Peter's Engineering College and extended very hasty vote of thanks to today's our resource person KV Vidyanandan sir. Thank you sir. Thank you very much. I express my sincere thanks to sir giving an excellent information about the energy issues in 21st century, world power generation capacity, world renewable energy sector wise, and also installed capacity and the target of India up to 2022, and also solar PV system. In that PV system, solar cells, put as the solar physics and PV modules and technologies, crystalline technology, thin film technology, and also grid connected PV systems, and what is the impact of temperature and PV cells, and also types of energy storage systems, and finally V2G and G2V technology also. So thank you sir, thank you very much, and thanks a lot for readily accepting our invitation. Thank you sir, thank you very much.
Okay, once again, thank you so much for giving me this opportunity. Okay, so I am hanging up.
Yes sir.
Leaving the meet. Okay, thank you,
Yes.
sir.
Thank
Thank
you.
you, sir. Thank you very much, sir.
Thank you.